Hi, I'm Doug Baldwin, and I'd like to welcome you to this mini lecture on the meaning of the word algorithm. This lecture is intended to introduce the term to viewers with no previous experience with algorithms or programming. I hope you'll like it. The broadest definition of the word algorithm is that an algorithm is simply a procedure for solving some problem. So if you know an algorithm, you can feed the problem into it and get a solution out. It's certainly useful to have ways of solving problems, but what makes algorithms really important today is that every computer program is an algorithm, or a set of algorithms, expressed in a form that a computer can follow. Algorithms are thus key to understanding what computers can do and to writing or understanding programs. There are lots of fine points to this definition that need to be fleshed out. First, I should say exactly what a procedure is. When I talk about an algorithm as a procedure for solving a problem, I mean that an algorithm is a set of instructions, a set of steps that someone or something can follow in order to find a solution to the problem. The steps have to be what are called effective ones, meaning that whatever is following the instructions really can carry them out. For example, add 1 and 3 would generally be considered an effective step because anyone can be expected to be able to do it, or at least be trained to do it. On the other hand, win the lottery is not an effective step because no one has a surefire way of doing it, so it can't be carried out on demand. The steps in an algorithm also have to be what are called definite, meaning that there is no uncertainty about what they mean. The previous add 1 and 3 example is pretty definite, whereas the famous direction "Go west, young man" is not, because it is unclear how far west one should go and whether one is supposed to stay in the west after getting there. I also need to say a little more about problems. Non-trivial problems have inputs that indicate exactly what instance of the problem is to be solved. For example, a problem might be to add two numbers, in which case the inputs would be the actual values of the numbers to add. Then adding 3 and 12 would be one instance of the problem, adding 18 and 6 would be another, and so forth. An algorithm that solves a problem thus also needs inputs, so that it knows what instance of the problem to work on. Finally, algorithms produce solutions to problems in the form of outputs, i.e. numbers, pieces of text, pictures, or other information that describes the solution to the problem instance that the algorithm was working on. Having outputs imposes two more restrictions on what procedures count as algorithms. First, an algorithm has to be a finite procedure, i.e. it has to produce its output and stop after a finite amount of time. This means, for example, that procedures that involve blindly guessing solutions aren't algorithms, because one could keep making the same wrong guesses forever. The second output-related requirement is that the output produced by an algorithm always has to be a correct solution to the problem. This requirement seems almost too obvious to mention, but in fact lots of useful procedures don't meet it. For example, if a word is in the dictionary, then and only then it is spelled correctly, is a useful enough way to check spelling that it is the essence of just about every computer spelling checker. But it doesn't pass the always correct test for being an algorithm to solve the problem of making sure that a document has no misspellings, because no dictionary contains every technical or slang term, nor can a dictionary catch misspellings of one word that turn it into another. This is why your spelling checker sometimes rejects words that are okay in a particular context or accepts ones that aren't. Procedures that are useful but don't meet all the requirements for being algorithms are called heuristics. As an example of a problem in an algorithm, suppose you can measure the diameter of a circle and you want to know its area. So the problem is to find the area of a circle given its diameter. Parts of problem descriptions that use such words as given or if you know or similar phrases usually identify the problem's inputs, and this example is no exception. So the input to this problem is the circle's diameter. Next we need some steps that calculate area from diameter. There is a formula from geometry that says the area of a circle equals pi times its radius squared. In this problem we have the diameter, not the radius, but we can calculate the radius as half the diameter. These ideas provide a complete set of steps for the algorithm. First, calculate the radius as the diameter divided by 2. Then calculate the area as pi times the radius squared. This algorithm's output is the area from the second step. Notice something interesting about the steps in this algorithm. I wrote them as if there were two, namely divide the diameter by 2 and then calculate pi r squared. But you could just as well see this algorithm as having 3 steps. One to divide the diameter by 2, one to square the radius, and one to multiply by pi. And, in fact, if someone wasn't sure how to do this arithmetic, even it could be broken down into simpler steps. This is really another way to look at the requirement that steps be effective. They can always be described in more and more detail until reaching a level that the person or machine performing the algorithm can do. Programmers find this tremendously valuable because they can start by describing an algorithm at a level appropriate for themselves, and only when they understand the algorithm at that level and believe that it solves their problem do they need to worry about expressing the steps in the greater level of detail that a computer needs. This idea that programs are just algorithms expressed in a particular way has come up a couple of times, so let's look at what the area algorithm would look like as a program. I can write it as a so-called function in MATLAB, a language often used for mathematical problem solving, like so. I don't expect that this program makes complete sense to you, but hopefully you can see some connections between it and the algorithm. That, in fact, is the point. Even without knowing the programming language, the fact that you understand the algorithm, which is independent of language, allows you to get some meaning from the program. Furthermore, because you know what steps are in the algorithm, you might even be able to learn something about the programming language from seeing how it expresses the algorithm. For instance, you might guess that the name spelled pi stands for the constant 3.1415, etc., or that the caret character means to raise a number to a power. This ends this introduction to the word algorithm. You have seen that an algorithm is a series of doable and unambiguous steps for solving a problem. Given inputs that identify the specific instance of the problem to solve, following the algorithm's steps will, in a finite amount of time, produce outputs that provide a correct solution to the problem. Algorithms are important in computer programming because every program is really just an algorithm written in a form that a computer can understand, but developing the algorithm in a form that people understand first, and only then translating it into computer form, is usually much easier than writing the computer form from scratch. Thank you for watching this lecture. I hope you found it useful.